All right, today we're going to start talking about inverse trig functions. We've been talking about trig functions up until now, and the idea was that we had been given an angle, and we found, or we've been given a point on the unit circle or something like that, or in space, and we were finding the tangent and the cotangent and the sine values and things of a specific angle. Everybody with me on that? That's what we've done so far. Now we're basically going to be working backwards in that. That is to say, we're going to be given a trig value, right? This is tangent of some angle, and we're going to be finding the angle that it came from. So the first thing we need to talk about before we can talk about those inverse trig functions is the idea of what an inverse function is. And the first issue is that an inverse has to have this feature being one-to-one. So let me start there. One-to-one function. So this is a function where every range value corresponds to only one domain value. And for a moment, let me draw your attention to an example, a counterexample, an example that this doesn't hold for. So do you guys remember the curve x squared? The basic parabola, right? It's one of those real standard ones you see way back in Algebra 2 and beyond. And it has the feature that there are two x values for every y value, right? So if x is equal to 1 and we square it, 1 squared is 1. But if x is equal to negative 1 and we square it, negative 1 squared is also 1, right? So it doesn't have this feature, right? Because there are two x values that correspond to that one range value of y equal 1. Now, visually, what you did when you first learned about one-to-one functions is something called a horizontal line test. Now, there are two line tests. There's a vertical line test, where you dropped vertical lines down, and when you did that, you were trying to decide if things were functions. And then there's a horizontal line test, and the imagery you want to have is dropping horizontal lines through the middle of your functions. And if it crosses the function in more than one place, it's not one-to-one. Okay? So that's the horizontal line test. So any horizontal line will intersect the graph in at most one place if the graph or the function is one-to-one. And there's notation for this. So the notation looks like a little negative 1, kind of like an exponent. It is not an exponent, but that's what it looks like. That's how I force the computer sometimes to let me do it, right, on my notation, as I act like it's an exponent. And what this is actually all yx such that x, y belongs to f. So what do you notice about this description? What literally happened? Yeah, Brad's doing it, right? We just flipped it around, right? We moved the x and the y. We switched their locations. We switched to the ordered pairs. And that's literally what happens. The inverse is literally switching the ordered pairs x. So all the x's become y's, all the y's become x's. Now, if you think about most graphs have this connected feature, the ones we're looking at anyway. And so I don't have just a finite number of things I actually switch, right? I don't have a finite number of points on my graph. I have an infinite number. So I don't literally write out every ordered pair and switch them. I'm going to do other things to find them. But that's what the idea is. There is one note that I want to make. This is not 1 over f. So you've seen the idea of putting a negative on something and it flipping something upside down, right? And you did that in a specific case, and it had to do with reciprocals, and it had to do reciprocals when you were working with inverses. But this is not an inverse that's a reciprocal, okay? So don't get confused. You can't do 1 over in your calculator. However, your calculator will have some notations that are going to be friendly to be able to use. So we're going to talk about our 3 primary trig functions in this section, which is sine, cosine, and tangent. 3.2, we'll talk about the other 3 trig functions, okay? But this is sine, cosine, and tangent. And the first thing that we need to remember as we're working here is what our graph of sine looks like. So when I'm looking at my graph of sine, I actually have something like this. I go from 1 to -1, or -1 to 1. I hit the graph in the middle at the x-intercept at the origin, and I go up to a peak. Come on. There we go. I come back down to the x-axis, and I go down to a minimum, and then back up to the x-axis. And I realize I haven't labeled anything, so let's go back and do that. This was at pi halves, at pi, at 3 pi halves, and at 2 pi. And the graph connected like this. And it did the left-hand side just as much. I'm going to only graph a little bit of it because I don't really need this whole graph. But it would continue on the left-hand side the same way, and of course at negative pi halves and negative pi and so forth, right? So there's 2 things that should be sort of screaming at you that are inconsistent in what I've said thus far. One is that this phrase up here at the top says inverse sine function, right? I've drawn a graph of sine. This right here is y equals sine x. But I told you on the previous slide, when we talked about it, 2 slides previous, that we were going to be dealing with inverse functions, and inverse function had to do with this idea of being 1-to-1, right? Horizontal line test and so forth. The only time a function has an inverse is if it's 1-to-1. And it should be raising red flags in your head, because this graph is not 1-to-1, right? If I draw a horizontal line, even through what I've drawn thus far, which is not the whole graph, of course, I'm going to be failing the horizontal line test, aren't I? Oh yeah, big time. Yes? There are points of this graph that I've already drawn so far that I crossed the graph 4 times. And I'm supposed to only cross it once. Are you with me? Okay. So in order to talk about inverse trig functions, we have to limit the portion of the graph that we consider. Right? It doesn't mean they don't exist. It just means they only exist on a portion of the graph. So here's what we do. For sine, we cut sine right here, and we only look between the red lines. Okay? Between the red lines is the graph 1-to-1. If I only look, okay, that wasn't what I wanted. If I only look from here to here on the blue part of the graph, can I draw all the horizontal lines I want and it only crosses the graph at one point? Sure. Or no points at all if I draw them far enough down or far enough up, right? Yeah, that's true too. So this portion of the graph is 1-to-1. So this is the portion upon which we will be defining sine. So a couple of features. So this is, let me write down what I said, a little bit of it anyway, 1-to-1 when negative pi is less than or equal to x is less than or equal to pi halves. Okay, in other words, between my red lines, which is negative pi halves to pi halves, I've got a one-to-one function. So sine inverse of x will be equal to y. That's going to be my inverse function. Now we said on the slide before, and this one really was the slide before, I'm not lying, it said that when we do inverses, we switch x and y, right? And we did it sort of an ordered pair picture. But literally, we do that, right? Now, you guys worked in the last three sections of the last chapter. Every time you drew a graph, it asked you for the domain and range, didn't it? Yeah, it did. And it did that in part because of what we're doing now. So I want you to think, between my red lines, what is the domain between my red lines? What does domain mean? X values. What x values do you see between the red lines? Negative pi over 2 to pi over 2. Some of you are answering my y values. X values go from negative pi over 2 to pi over 2 between my red lines, right? That's the domain, the x values of sine. And when we do the inverse, it switches. Those are x values for sine, which means they become the y values for inverse sine. So the domain for sine becomes the range for inverse sine. X and y are supposed to switch, right? So that means the domain and the range switch as well, because domain is x and range is y. That's what we're doing. We're switching the domain and range. So the domain for this new function up here, we'll get that one in a minute, but my range is negative pi halves to pi halves. Or you can write it as I did below down here, right? This is an interval notation. Sorry, this is an inequality notation. This one up here is an interval notation. Okay? My domain for sine between my red lines was negative pi halves to pi halves. So my range for inverse sine is negative pi halves to pi halves. Now let's go back to the domain of the original function, the picture that I've got. Between my red lines, what's my range? Negative 1 to 1, right? So my range on the original graph was negative 1 to 1. That means my domain for my inverse sine will be negative 1 to 1. It's backwards. Are you guys okay? Because we're about to do the same thing for cosine. Okay? All right, let's take a look at cosine then. Let me make one comment. I mean, your book doesn't do this, but I feel like you have to see it, because if you ever ran into this, and you will for some of you run into this later on, another way of writing this inverse sine here is arc sine. Sorry, that negative shouldn't be there. Arc sine of x. Your book does not use this notation at all in this section. At least I didn't find it anywhere, which is unusual. Most trig books will use both notations interchangeably. Not because you really need both of them, but the nice feature about writing it as arc sine instead of sine with a negative 1 is you don't have any sort of intuition of thinking this should be 1 over. There's no division, sort of an idea conflicting there. It's also kind of nice because when you see the word arc, you're thinking, oh, I'm going to be getting an angle when I'm done, because this is an arc, right? The arch of what's going on. So you kind of have this feeling of an angle going on. But your book doesn't use that. Again, I'm mentioning it because those of you who do go on to calculus, you need to know that, because most books will use that notation as well. Okay, let's look at inverse cosine. So we're going to draw the same graph we did before. That is to say, we're going to draw a graph of cosine. So my graph of cosine has the feature that it starts up here at a value of 1, it comes down to a value of negative 1, and it starts at a peak. It comes down to the x-axis at pi halves. At pi, it hits a minimum value. Continue the graph over here at 3 pi halves. That doesn't look like 3 pi at all. Let's try again. We're back up at the x-axis, and then at 2 pi, we're back up at a peak. And of course, we have the same graph going on the left-hand side of the curve. I'm not going to draw it because I don't actually end up needing it. But even as much as I've already drawn, you can see it does not pass the horizontal line test, right? Kind of like a parabola almost in the same issues that it's going to have, just this portion drawn. So we need to put in those red lines like I did before. All right, so we actually end up putting the red lines for cosine at the y-axis and at pi. And if you take a look, sure enough, between the y-axis and pi, I have something that's 1 to 1, right? Yeah? So that's the thing I'm going to write here at the bottom first. So the graph is 1 to 1 when 0 is less than or equal to x is less than or equal to pi. So I do have a cosine inverse, or an inverse cosine equation. We'll say y equals inverse cosine. And again, alternately, this would be written as arc cosine in some books. And I want us to identify the domain and range. So let's do the domain actually first. So if I want the domain for inverse cosine, that's the equivalent thing to asking what is the range for cosine. Between my red lines, what is my range? -1 to 1. So my domain for inverse cosine is -1 to 1. All right, so let's look at range. My range for inverse cosine is equivalent to my domain for cosine. What is my domain for cosine between my red lines? 0 to pi. And this is really important because you will notice it does not match sine, does it? No, it doesn't. Sine went from -pi-halves to pi-halves, and cosine goes from 0 to pi. And as we're working with these problems, we have to keep that in mind. It's kind of like keeping in mind that the period for sine, cosine, secant, cosecant was 2 pi, but the period for tangent and cotangent is only pi, right? They are different. Last one we're going to look at then is tangent. Now tangent's really different because its graph is really different, but in some sense it's actually a lot easier because the graph lends itself well to knowing exactly where my red lines should be. So let's take my graph and draw it first. All right, the graph of tangent has asymptotes. Do you guys remember that? Oh, good. That's good. And it has these asymptotes occurring something like this. What were the values they occurred at? Do you remember? -pi-halves and pi-halves, right, Michael? Yep. All right, and then we actually had an x-intercept at the origin. Tangent, is tangent increasing or decreasing? It is increasing, and it looks something like this. So this was the graph of y equals tangent of x. And I'm not going to draw anything else, because anything else I draw is going to make the graph not 1 to 1, isn't it? Yeah. So this graph, exactly how much of it I've drawn already, tells me exactly that if I wanted to sort of draw those red lines in, they would be at the asymptotes, wouldn't they? So now, all of a sudden, I have a tangent graph. So tangent of x is 1 to 1 between -pi-halves and x and pi-halves. Notice two things. Number one, notice that those are the same values for sine, right? So sine and tangent have the same pi-half, -pi-half values. Part of why they do that is those even-odd properties. Tangent and sine were odd functions, right? Yeah? This is what's going on here. Cosine wasn't. It was not odd. It was actually even. And so it had a different sort of a look to it because of that. There's also one other thing to notice here, though. How is this different than what I just wrote down 2 minutes ago or whatever for sine? It doesn't have the equal to. Janet, why? Do you know? Because it has asymptotes there. That's why. So I can't actually equal those two because those gave me the asymptotes. So that is something a little bit different. And there may be a typo depending on when you printed your paper, because there was a typo when I typed something else later. So I'll draw your attention to it to fix it if that's the case. It's later in the packet here. But let's write down what we've got so far. So this does have an inverse function. So this is y equals tangent inverse or inverse tangent of x. Let's start with domain. The domain for inverse tangent is the range for tangent. What is the range on this tangent graph? You got it. Negative infinity to infinity. Or you can say all real numbers, right? We did that before too. That would be fine. Some of you like that notation. Range, okay. My range values for inverse tangent are my domain values for tangent. What is my domain between my red lines? Negative pi halves to pi halves. And if you're going to use interval notation on this, I need parentheses this time. Yes, I do. And that's different than a sine. Sine had brackets. Well, there's two questions inherent in what you just said. So parentheses mean I can't equal a value. Okay, so that's why I'm going to use the parentheses. And I can't equal those values here because of the asymptotes. So yes, it is related to the asymptote issue. Okay, we're going to do a couple of examples. Well, you know what? Let's do one example before we leave so you have a feel for what we're going to do with this, okay? All right, example number 1, and we'll pick back up with example number 2 next time. This says cosine inverse of 1/2. How do I handle this? Well, here's how you handle it. You're going to say that this equals an angle. And the easiest way for me to remember that it equals an angle is to use theta. Because we use theta every time we talk about angles, don't we? Okay. What this does allow you to do then is to rewrite this. And I want to see the rewriting. Okay? Because that tells me that you know the relationship here. This allows you to rewrite this as cosine of, yes, Michael, cosine of theta equals 1/2. Those are equivalent expressions. Inverse cosine of theta, inverse cosine of 1/2 equals theta means cosine of theta equals 1/2. And here's where your unit circle comes into play. All right? You have to remember where on your unit circle cosine is equal to 1/2. So cosine is either x or y. It is x. It's the x coordinate on the ordered pairs x, y. Where do you have on your unit circle an x coordinate that's equal to 1/2? At 30 degrees. At 60 degrees. Yeah, it is at 60. But we're working with real numbers here for angles. That is radians. This is at pi thirds. 60 degrees, pi thirds, pi over 3. Now here's the deal. There's one other location that you could give me. It's actually at 5 pi thirds, I think, all the way down here in quadrant 4. I can't use quadrant 4 values, and here's why. What was my domain? Why isn't it there? I don't know. All right, things are missing.